Thank you. Thank you very much. Good morning, everyone. Thank you very much for inviting me and for having me. Thank you to the organizing committee for everything. Yeah, so a few things about me. There you go. There we go. So yes, I'm affiliated with RIKEN. There we go. I'm affiliated with RIKEN. RIKEN is a research institute in Japan. If you're not familiar with it, I think the easier way to think of it is like it's the Max Planck. So it was actually built on the image of the Max Planck. So there are several centers across the country, and then each one of them focuses on a different disciplinary of science. So this is the map of Japan. So there are several institutes, centers across the country. A lot of them are based in Tokyo, and then there's some of them based in Kobe. So I'm actually based here in Kobe, which is a city next to Osaka. And it's very famous for Kobe beef, if you're familiar. So there I'm affiliated with RCCS, which is a Computer Science Institute. And then I'm also co-affiliated with another institute in Tokyo, and that is called NITMB, and it stands for Interdisciplinary Theoretical and Mathematical Sciences. So RCCS is a computer science institute. So a lot of people, work with high performance computers, quantum computers, but there are also a lot of people that do applications and simulations like myself. One thing that is really cool about the institute is we have a very big computer. Its name is Fugaku. We actually have a little room that you can see it. It's a very beautiful computer. It used to be one of the fastest supercomputers in the world, not anymore. They're building a new version, which will be Fugaku next. But still, like this machine has like 8 million cores, right? So, you can run very big, large simulations on this machine. In ITHEMS, I'm affiliated with the social science team. So I work with one person that some of you might know. His name is Yosuke Murase, and he just started a new team in ITHEM, which is called Mathematical Social Sciences, and I work with him. We now have a website, so if you're interested in our team, please check it out. So what do I work? I work with direct reciprocity models, mainly. And what does direct reciprocity stands for? So how we model direct reciprocity is we have these games that you have blue and red, but now they just don't play one game where they decide to cooperate or defect, but they play this game over multiple rounds. And why this is interesting is now because blue and red can kind of like condition the behavior based on the past history that occurred. And then we can have very complex behaviors for red and blue. And a lot of times the questions that we ask is, for example, what are with an asequilibria here? What should blue play, such as, blue is like an asequilibria. But then obviously the one question, and Otsuki spoke about this yesterday, okay, we have this now. Now the question is like, how do we get to them? And the way that evolutionary models of direct reciprocity address this is by considering a population of individuals. So Kristen already gave us a nice introduction to some of this process, yesterday. I will repeat it for the people who are not here, and also to kind of like lay the baseline of this is what I mean when this is my baseline process when I talk about this. What do we do? So we consider a population of individuals. They have different colors. And then there are like the game dynamics. What happened on the game's dynamics? We match two people together. So here, for example, we match blue and green, and then they play this repeated game. Because they play this repeated game, they need to decide what they do at each turn. And we say that this is defined by the strategy. So the strategy determine behavior from observations of past interactions. And one very famous class of such strategies, for example, is memory end strategies. So blue here needs to make a decision in this turn. So blue would look at the past history, and based on what has happened on the tuple, it will react to it. And then what we do is like we match each individual, like we take all the possible pairs because we consider a well-mixed population. And then at the end of this, we say that everyone has a value, right? It has a fitness, which is, let's say, the average score of what they achieve from all their interactions with everyone else in the population. So this is the game dynamics, and then we have the evolutionary dynamics. So what happens is like, okay, at each time step, so we consider this population, and then at each time step, we select one random individual from the population. In this case, it will be blue. I really like blue. And then two things can happen. Blue can either mutate, and Blue is going to say, I'm going to randomly sample a strategy from all the possible strategies that I can play, or I'm going to change, but I'm going to learn. It's going to be more of a learning process. Or I'm going to learn not just randomly, but there will be some rule in how I'm changing. So we say with 1 minus m, mu, this is mu. With 1 minus mu, imitation happens. What does happen at the imitation level? Where we have blue, and then we select another player from the population. This time it's red. And then we say this is the learner, this is a role model. And then with a given probability, blue will imitate red strategy. And this depends on the Fermi fraction, and we already saw this yesterday. Then we run this process for many time steps, right? We keep running it, and then at the end of it, we just measure some things. For example, we measure what the people in the population played, like what is the most abundant strategy. And one thing that we measure a lot and we care about is how cooperative is the population, right? Because we want to ask questions, does cooperation evolve? Because cooperation is a good behavior, we want it to evolve. So then we measure like, oh, what is the average cooperation rate of the population? And then we say, okay, it's this. Is it higher than what we expected? And what promotes cooperation? And then we will change some assumptions. We will include some things, and we see how this changes the evolution of cooperation. So this is our basic model. And then as any model, it comes with assumptions. And one set of assumptions has to do with our individuals. So take blue here, for example. During this process, I have made many assumptions about blue. For example, I've made, some of the assumptions like how much blue can remember, how much information blue has, and how blue learns. And a lot of my work has been about understanding these assumptions. So what happens if we relax them? What would be then their effect, for example, in the evolution of cooperation? So today I will talk to you about some projects that I have done in the past, mainly on the questions of how much blue can remember, how much information blue has, and then how blue learns. I will very briefly go the results of the first two projects. So these are projects that have already been published. And then I'll touch upon the last one for a bit, which is something new that I started working on recently. So it's just mainly to say this is what I'm playing with right now. So if you're interested, please talk to me about that. This one's no feedback anymore. So let me start from here. How much blue can remember? So like I said, so we have these strategies. And then I said, that we defined a lot is the memory n set, right? So we say, okay, given the past n interactions, the past possible interactions that have happened, how do you react? But usually we don't consider memory n strategies. We actually usually consider memory one strategies. What is the reason of that? Well, it's because the space of the strategies increases as we allow for more memory. Like, of course, like this is not a bad assumption because yes, it makes mathematical tractability, but also because like if we go to 250 like vectors, what does it even mean, right? Like how can I interpret a 256 vector? Like if you ask me what does blue does there, I'll be like, I'm not sure. So I'm not saying that this is a bad assumption. I understand where it's coming from, but we still want to understand what happens when we allow for more n. So what we did with this project is we managed to look into higher dimension strategies. And the way that we did this is by not considering memory n strategies, by considering a subset of them. We call reactive n strategies. So memory n will look at the entire history and react. Where here, I'm only going to look at my co-player. So blue thinks that blue is a very good person. What does it mean to be a good person? Blue doesn't necessarily care about what blue does. He only cares about what green does. Right? So I'm only reacting to blue's history, and we call these reactive strategies. Does the space of reactive strategies increases? Yes, of course it does. The vector also, increases a lot, but it just increases a bit better than it does in the memory n case. So here, at least we can do a few more things, and we argued also here we can interpret at least the behavior a little bit more than if we were in the entire space of memory n strategies. So by focusing on reactive n strategies, what we actually managed to do is we derived an algorithm, a very elegant algorithm. Then you can give me any n, any game, and then I could characterize for you Nash equilibrium. And just to show you what this looks like, let's consider the case of reactive 2. So in reactive 2, I'm reacting to what you did. So it would be you cooperated twice, you cooperated once and you defected once, and then you defected twice in a row. And I'm going to say, okay, I want Nash equilibrium that sustain cooperation, right? So if I play this, then I'm always going to be at CC. So I'm just going to set PCC equals to 1. I'm going to give it to my algorithm and say, what are the Nash equilibria? And it's going to say, these are the conditions that you need to uphold for you to be a Nash equilibrium. And then what's cool is this is what the space looks like, for example. And then I'm plotting this for a specific game. So you give me a game. Well, here you don't need a game, but you give me a memory and I tell you, hey, this is what it is. So these are good Nash equilibria, cooperative Nash equilibria. We can also have defective Nash equilibria. So for example, now if I play this, I'm always at the DD state. And again, we say memory 2, set this to PDD, give me the conditions. These are the conditions for you to be Nash, right? So we get nice explicit conditions. We can even push to memory 3, and we still get nice linear conditions. And what's quite nice is they're roughly interpretable, right? They're not the most mind-blowing conditions to look at. But why we're interested in these things? Where, for example, one thing that we can look at is how does the volume of these things change as we allow for more space, right? So here what I'm doing is I'm just allowing for more memory, and I'm saying what is the relative volume of defective and cooperative Nash equilibria. And then you can see in memory N, like this is very high, so you're more likely to land on a defecting nice equilibrium. But then as memory increases, there's a very significant drop in the volume of these things, where cooperative drop a little bit more like smoothly. So what happens here is, in the case of memory 2, if you were to randomly select for bad strategies and good strategies, you're more likely to land on a cooperative nice equilibrium. And this is true for any cost. And where does that come into play? Because actually, when we run evolutionary simulations, if we go back to the model I talked at the beginning, we allow for memory 1, for reactive 1, reactive 2, reactive 3, and we run these simulations independently for different parameters. What we see is that the blue line here is always higher than the other lines, which means that you get a bit more cooperation where allowed for higher memory. And then the question, okay, what is driving this? And then we can see how often are you on good Nash equilibria? And we can see that these two things like match. So here cooperation is high because I get to cooperative Nash equilibria, I stay there. And why do I get here? Well, arguably because you're more likely to get there than to get on a defective one, than when you were here, for example. So we know that this volume of things actually drives also the evolution of cooperation in the evolutionary simulations. This is not necessarily new. This is actually, Stewart and Plotkin also had a paper that they showed for reactive and strategies that also they also discussed about the volumes of these things. But what I think is cool about this paper, it really is that we do get this elegant algorithm that allows us to fully characterize Nash equilibria if we want to. And here I only spoke about cooperative and defective Nash equilibria. But then the question happens, like, are there any other classes? And then if there are any other classes, do they become important in evolutionary simulations? And if they don't, why they don't? And actually right now we have a PhD student with Christian called Francisca, and she's actually working on these questions. So for multi-action games, she can show what other classes of Nash equilibria are they. Then we run evolutionary simulations. We don't see them always coming up. Actually, cooperative and defective Nash equilibria are very important. But then the question is like, why? And now we can actually look into these things with more details because we have the explicit conditions and we know what we're looking for. So please look forward to Francisca's work. So this concludes the first project that I talked about. So how much blue can we remember? And now one thing that I did here, and I cheated, I didn't cheat, but one thing that I did here was when I run my evolutionary simulations, I say, oh, my population will play reactive 1, my population will play reactive 2, my population will play reactive 3. And then there's an important question is like, does it make sense to restrict yourself to a specific strategy set? Well, the answer, Philip has it. And then Philip will give a talk later today about this. And it's a very interesting question, right? Because we make this assumption. And the question is like, how restrictive is this assumption? Are we missing something? And Philip did some amazing work on this to tell you when you're allowed to do this assumption, whether the restriction really affects your result and it doesn't, to put it nicely. But Philip will talk about it in more details. So if I didn't do you justice. So the next question was, how much information blue has? So we talked about the game dynamics, and in the game dynamics, I said, oh, we restrict blue to have memory 1 strategy, and when we relax this. But now we're going to go to the other level of the process. And that is the evolutionary process. The evolutionary level? The evolutionary level. So here what happens, blue needs to imitate red. Blue has a value, red has a value. And then the way that we assume that blue knows their value is by saying, okay, you interact with everyone in the population for infinitely many games, and you calculate your expected payoff. So we assume blue to remember everything and everyone and every single interaction they had with them. But then we also say, hey, blue, but when you play in your repeated interaction, you're allowed to have memory 1. Now, this is a contradicting assumption, right? Because when I need to know my value, I remember about everything that I've done with all of you. But when I play with you, I only remember like what just happened like yesterday. So this is a little bit of a contradicting assumption. And we just wanted to relax it and see what happens. So this is actually a work. Oh, my coins appeared. And this is a joint work with Alex and Christian. And what we did here was like, okay, let's take then the complete other extreme. So here you remember everything and everyone. What if now we consider you remember only one interaction where you had with one person in the population? And the way that we did our framework, it was actually quite nice because it was nice to extend it. So then we can take all the possible combinations of like one person, 2 turns. One person, every turn. We can take 2 people, 1 turn. Or 2-2. So the framework it was easy to extend to these cases. So what do? We consider each one of these combinations. We once again run the evolutionary process. And this is what the results look like. So these are the results for the standard case. So what I call the perfect payoff memory. You remember everything and everyone. We run the simulation for these specific values of parameter values. We get a very high cooperation level, like 97%. Great. If you only consider what happened with one person or one interaction, this significantly drops at 50%. There's still cooperation, right? 50% is still, yay, it's not bad, but it has decreased. What is interesting is as we allow for slightly more information, we can see that these bars very quickly approximate the perfect assumption, right? And here I'm just considering, well, this is a nice case, because I'm only considering 2 people with 2 interactions, and already I'm like 90%. So at least when you allow for slightly more memory, this bar seems to approach the classical limit very quickly. And why is this cool? Well, this is cool because cooperation can still evolve with limited memory. Obviously, like we saw that, you still get 50%, is not the worst. But actually what I find really cool, it is actually how these things increase so much. And why do I find it cool? Because imagine now that I have this process that I need to simulate everything. There's no analytical expressions. And I need to calculate the expected payoffs. But this paper tells you don't really need to calculate everything with everyone. Maybe if you just sample just a few of them in a few turns, you will be already here, right? So it just makes the evolutionary simulations a bit easier because it just shows that we can approximate this, maybe by just randomly sampling a few individuals, playing the game with them repeatedly. We're going to get these bars just increase so quickly. So again, just to summarize what we saw with this project is we took this assumption at the evolutionary level where we say, oh, you remember everything. And we say, what if you don't remember everything? You remember 1 thing, 2, 3 things, 4 things. And we saw that cooperation still evolves, even with limited payoff memory. And then as individuals remember more of 3 recent interactions, the cooperation rates applause the classical limit. And with that brings me to the end of the first 2 projects. Like I said, these 2 projects are out there. So if you're interested, please let me know. And I can share the paper details. They're actually on the last slide. And I'll talk to you a little bit about the last one. And like I said, the last one is work that I'm doing now. So feedback is welcome. And it goes a little bit to how does Blue learn. So Christian yesterday talked about his model. And then again, right here, we make assumptions that we give beta, for example, a value where Christian says, what if we allow this beta value to kind of evolve? I'm going to go even a step further. I'm going to say no further before. I'm going to say, okay, here we always assume that Blue does like this social learning, that it considers a population and selects someone and then it does something. But then what if Blue actually does individual learning? So going back to Christian's talk, we have introspection dynamics. We have this process that now I'm in a pairwise interaction and I learn not by imitating my co-player, but by thinking what would happen if I were to switch. So this is really an internal, self-centered is not the right word, is an individualistic kind of idea, right? Where here is like, oh, a lot of people, something, red is doing something good and I should learn from red, where the other one is like, what should I do maybe to be in a better stand? So my question is like, what is the difference when we compare these 2 dynamics? And I'm going to do this for repeated games now. So I'm going to consider like a low cost of cooperation, medium cost, and high cost. And what we get here is I'm changing the selection of beta, so how likely I am to learn to imitate someone. And I'm also going to change, it's going to appear in a second, I'm also changing the error rate, right? So when I play my strategy, there's an error rate that my action might get flipped. And these results are known, right? For low cost, we see a lot of cooperation. Great. For medium cost, there's like, it depends on the parameters. For high cost, defection kind of takes over. So what if we allow for introspection dynamics? And this is actually what the results look like. And if we were to plot the difference, the white is the only region where these things 2 match, right? So what we see is for the medium cost error, which is the interesting case, here you can see that they only match in a very small region. Why? Well, we know what drives the dynamics in the classical case, right? Here I'm considering memory 1, so we know what drives the dynamics here because we know, for example, for low cost, cooperation evolves becomes win, stay, lose, shift, kind of like takes over. Everyone plays like win, stay, lose, shift. And here again, the region that you have cooperation is the region that win, stay, lose, shift is abundant. What happens in introspection dynamics? When is win, stay, lose, shift? And here is the entire population plays win, stay, lose, shift. And here for introspection dynamics, I need to consider all the possible pairs, right? So here the station distribution is like me and my co-player playing win, stay, lose, shift. Where there is the entire population plays win, stay, lose, shift, just to make that clear. And then we can see that again, yes, in this region, things match. But let's look closely here at this region and see what is happening and why do we only match here. So I'm just going to take that line, and this is pretty much what I'm plotting. I'm plotting for the error rate. I'm plotting the stationary distribution. So how often are we in both players playing Wunsch-Taylor shift? And you can see the probability is very low, but then when the error rate becomes very high, it kind of like increases. But why? What is driving this? And then the question we ask here is, for example, if I am in Wunsch-Taylor shift, what kind of invades me? What are the other states that I can get to? And then we can see that the states, regardless, like here and here, is the states that one of us changes when it goes to 1, 0, 1, 1. So we're both playing Wunsch-Taylor shift. One of the strategies has an incentive to change and play this strategy 1, 0, 1, 1. Is this a famous strategy? I actually don't know. It's the first time that I started paying attention to this strategy. But why? What is it about that 1, 0, 1, 1 that kind of invades? So let's compare again the two processes. We have the pairwise and the introspection dynamics. And what I'm plotting here is the probability to change to this strategy. Here is in the population level. What is the probability from being to a Wunsch-Taylor shift population changing to 1, 0, 1, 1? And here is in the introspection dynamics. Here, negative is 0, great. Here, positive, then drops. Why? It has to be dependent on the payoffs, right? So let me plot the payoffs that the processes take into account when we're calculating this. So here you're calculating the expected payoff, right, of Wunsch-Taylor shift population, and what happens if a mutant 1011 comes in, and then the number of mutants. So we can see that the payoff of me playing Wunsch-Taylor shift as the entire population level is always going to be higher than the entire population playing 1011. But if we look at the pairwise payoffs, for this region, our payoffs are pretty much the same, and then they start to differentiate. So for a very big region of parameters of error rates, the payoff of Wunsch-Taylor shift against itself is exactly the same as the payoff that 1011 gets against Wunsch-Taylor shift. And this is why this happened. This is why we have neutral invasion. What is the 1011 strategy? Actually, before that, why? So the problem, though, is these things are the same, but this is low. What does that mean? I can invade Wunsch-Taylor shift when I'm 1011 because our payoffs are pretty much the same, so neutral invasion happens. But at the population level, if there are other people like play like me, this hurts me because I don't do well against myself. I do well against Wunsch-Taylor shift. I don't do well against myself. Why do I do well against Wunsch-Taylor shift? Because it goes back to this idea, like we have errors, right? And then why Wunsch-Taylor shift does well is because if an error occurs in one step, it recovers and it goes back to CC. What happens with this strategy 1011 is that the two things can happen. Either it will be exactly like Wunsch-Taylor shift, an error occurs and then it returns very quickly, or it will return in 2 steps. So either it takes 1 step or 2 steps. If errors are not so common, I guess like the payoffs are pretty much the same because then this happens with like low probabilities. But as you increase error rate, it's more likely that you also get this delay. And this is when the payoff starts to like, this is when my payoff starts getting like lower than Wunsch-Taylor shift. So what I'm trying to say here is this kind of weird strategy appears that kind of neutrally invades this idea, this Wunsch-Taylor shift that we had as a very robust strategy, and it still is a very robust strategy. But then what it helps Wunsch-Taylor shift in the pairwise comparison process, it really is the self-payoff. So in these processes, at least, the self-payoffs are important because it's only because 1011 does not do well against itself. So then, okay, the question is like, can we include this? So can we go back to now we had these 2 different processes? Can we just give it a population structure? And now when you update, you don't do imitation, you do again introspection, but now you have a population, so you interact with yourself again here, right? So now you can argue that self-payoffs also become important. What happens if we run the same process again? Well, they're closer. The blue things are more likely, more aligned. Obviously, there's still some difference in how we get to this. There's still some difference in the regions, but they look more alike. One question is, and we had it before also in the heat maps, what if we look a little bit higher? Because it looks like these are things are just shifted, right? So what if I allow for selection strength to also be a bit higher in this case? This is what it looks like. So you can see that, yes, now they look more similar, right? So it just like introspection dynamics needs a different beta, this a different scaling. So they look similar, but again, they're not exactly the same. And for example, what is very interesting, at least to me, is this very clear cut here, right? like you go really from defecting state to cooperative state, where there it just seems to be a more smoother transition. I'm not sure how much time I have. So then we again can like zoom in a little bit and look at what happens there. And then, for example, this is what the average cooperation for the pairwise and for the introspection dynamics. And like I said here, this is a very smooth transition that you just go to more and more cooperation. Where with introspection dynamic, it seems that, you know, you initially dropped and then you have this very like clear change of the dynamics. We can look at the strategies that are there. So we can see that in the pairwise comparison process, like we start with this, like, you know, coexistence, and then at some point, Windstyle shift, this is Windstyle shift, kind of takes over. Where here, you know, you just start with nothing is abandoned, then you have a little bit of coexistence, and then you have like this sharp increase. So here I'm just zooming in here to look what it looks like. And you could argue that again in this region, so if we just select for the selection strength, these things match a bit. But what is interesting here is Windstyle shift never completely takes over of the population, because 1101 is here. But what is interesting, I guess, about this is in the pairwise comparison process, the process really pushes us towards a homogeneous population, where in the pairwise comparison process, we seem to be getting a little bit more heterogeneity, which I think is cool. And with that, those were the 3 projects that I wanted to talk to you about today. Just to give you a summary, evolutionary outcomes depend strongly on our model's assumptions. So it's just nice sometimes to relax them and really see the effect that they have on our results and the interpretations. Memory formation and learning shape direct reciprocity. For the first project, what I showed you was this one: more memory expands cooperative collinear spaces and promotes cooperation. So I think, again, having this algorithm, there's a lot of things that we've learned by having this algorithm, for characterizing these NAS in higher spaces, which I think is really nice. And please look forward to Francisca's work in the future. And then, yes, we just show when cooperation can emerge and how the different learning dynamics kind of like, you know, change the evolutionary outcomes. There's a lot of work still here. There are a lot of things that I don't understand. So please feel free to talk to me about that. Yes. And with that, I would like to say, yeah, these are some of the publications I spoke today. I would like to thank my collaborators who are here, Philip, and Alex. And also, these are the people I'm currently working on some of the projects that I presented, Yosuke, Maria, and Francisca. And thank you very much for your time.
But we have one question while we transition to Josh. I have another question, but I'll just ask you this one. In the introspection dynamics, can you just tell us a little bit more about what that means? Like, so you consider one partner and you ask, if I had changed strategies to another reactive memory end strategy, would I have done better against that particular partner? Is that right?
So in the introspection dynamics, I say, so I consider memory 1 strategies, and then I say, yes, we're playing like this. I'm doing great. What happens now if I change and I'm still playing with you?
And when you ask that hypothetical, you must know my strategy to ask that question.
Yes, I do know your strategy. Yeah, because we're having the interaction. It's very clear to me what you're doing. And now I'm just like, oh, given that I am playing with Josh, would I do better if I was nicer? Or given that it's Josh, would I do better if I was exploitative, for example?
I have a follow-up question, but I'll delay it. Yeah, it's very interesting.